Okay, next we will discuss the Young double slit experiment. This experiment was performed by Thomas Young Thomas. In 1801 to prove the wave nature of light. In this experiment, he discussed the interference of light. As I already mentioned before, that when two waves are moving in the same direction and such that if this is one wave and we have another wave also moving in the same direction in such a way that the crest of one wave is on the crest of another wave and the trough of another one wave is on the trough of another wave. Like here the crest of this wave is on the crest of this wave, trough of this wave is on the trough of this wave. Then these two waves interfere with each other or superimpose it with each other in such a way that the resultant wave magnitude is bigger. The resultant wave magnitude is this one. So here we have the resultant. If I consider this wave to be y1 and this wave is y2, that is the resultant wave y, which is equal to y1 plus y2, and this is called constructive interference. Like the two waves superimpose in such a way that the resultant wave has magnitude which is greater than the magnitude of individual wave. We call it constructive interference. Next we have another type of interference in which if the crest of one wave falls on the trough of another wave, if this is one wave and we have another wave like this, here the crest of this wave falls on the trough of this wave, the crest of this wave falls on the trough of this wave, the resultant wave is a magnitude which is 0. If this is y1 and this is y2, then the resultant wave y, which is equal to y1 minus y2, which is a 0 magnitude. Like the wave disappear after superposition of wave in this way. We call it destructive interference. So similarly, if light also composed, light is a wave. So when light travels, two light waves travel in such a way, the crest of one wave falls on the crest of another wave, then we have a bright light. And similarly, if two rays or two waves of light move in such a way that the crest of one wave falls on the trough of another wave, then we have no lights here. So there will be a darkness. So it means that these waves, they cancel the effect of each other. Here they enhance the effect of each other. Here they cancel the effect of each other. Now, this is the experimental set of double slit experiment, Young double slit experiment. Here we have a source of light which emit light in this spherical wave in this form. Now here we put a screen A. In this screen we have a small slit here, small opening, which I represent by S0. Now once this light falls on this slit S0, I can say that light coming from the source, this source, illuminate slit S0, like it falls on this slit S0, which is on this screen A. Now this incident light, after passing through this slit S0, will pass through two another slits. This is these two slits are in the screen B. Here we have slit S1. There is a small opening. Here we have another opening which I call S2. I call this one is S1, this is S2. Now after passing through these two slits S1 and S2 on the screen B, what will happen? This light after passing slit S1 is spread in all directions. Similarly, the light after passing through slit S2 is spread in all directions. So we have two waves now. Here there was a single wave. It comes here, we use these two slits S1 and S2 to divide this single wave into two waves. So after passing through this slit S1 and S2, we have two waves now. One wave is this one and the another wave is this one. So they are spreading in all directions and they are moving in the forward way. So they are moving in the same direction and they are moving in the same medium. So on their way, what happened? They interfere. So the interference can either be constructive or it can be destructive. Whenever there is a constructive interference, then we have a dark region here. The dark region, I call it minima. And whenever they interfere constructively, like we have constructive interference, then on the screen we have bright spot, which I call maxima. So after passing the light through this slit S1 and S2, we have two waves now. These waves interfere with each other on their way in the forward direction. When they are moving in the forward direction, these two waves interfere. Somewhere they interfere constructively and somewhere they interfere destructively. Whenever they interfere constructively, we have a spot, bright spot, a light on the screen. Whenever they interfere destructively, then we have a dark spot, a minima. So the light spot is represented by this maxima and the dark spot are represented by this minima. So on the screen, if we see the screen, then on the screen we have maxima, minima, maxima, minima, maxima, minima. So this is called Young double slit experiment. From this experiment, we got the point that once light passes through this apparatus, so on their way they interfere with each other, because of the interference we have this maxima and minima, maxima and minima. Maxima comes from constructive interference and minima comes from destructive interference. So this experiment proved the wave nature of light. Now the point is, here this experiment shows that interference of light occurs, and we know that interference is a wave property. So we conclude that light is also a wave. Now we will find out that when this maxima comes from, when this minima comes from, when this maxima occurs and when this minima occurs. We will prove this now. For that, I consider again a single slit, a double slit, yes. Suppose we have, now suppose I consider this point, okay. I started from these 2 points. We have this screen. These are the 2 slits. One is S1, one is S2. And this light is coming from slit S1. Let's suppose this is the light which is coming from this slit S1. Now I consider any point on this screen. I consider this point on this screen. Now light after passing through this slit S1, S2 let's suppose, and this is slit S1. Let's suppose we have either a dark spot here or we have a bright spot here. Either we have a maxima or minima. Let's suppose one ray of light after passing this through slit S2 reached here, and one ray of light after passing through this slit S1 reached here. I call this ray as R2 and this ray is R1. Now if these two rays R1 and R2 they interfere constructively, then we have a bright spot here, a maximum here. If these two rays R1 and R2 they interfere destructively, then we have a dark spot here, a minima here. So I will find out whether this is minima or maximum. Now for that I consider this separation, like the separation between these two slits, the distance between these two slits. This distance I call it D. And I suppose that this screen B, which contains slit, and this screen in which we observe the dark and bright spot, they are at a distance capital D. So this capital D represent the distance between the slits and the screen, and this small d represent the distance between these two slits. Now I consider a reference light. I plot a line from the center of these two slits, S1 and S2, on this screen. I plot this line. This is D now. Now I consider a reference line which starts from the center of these slits to point P. Let's suppose this is the reference line, and this reference line makes an angle theta with this line. Now I call this point P, and now the arbitrary point, this point P, is at angle theta from this line. Here the angle is theta. Now the distance I will represent this as S1, this is S2. Now the distance S2P, this is S2, this is S2, I call it, this is S2. Now the distance S2P, this is point P, S2P is smaller than the distance S1P. Now S2P, what is S2P? It is the ray R2 which travel from the slit S2 to point P. So this S2P is the distance of ray R2 and S1P is the distance of ray R1. Now this distance R2, S2P is smaller than, this S2P is smaller than S1P. Now what I will do now, I can plot this figure again. I'll plot this figure again. Suppose we have this screen in which we have these slits. This is screen B and this is screen C, let's suppose. I suppose the distance between the slit and the screen is D, and I consider the distance between slit S2 and S1 is this distance, small d. And I suppose that we have a point here, a ray coming from this slit S2 meet point P here, and similarly a ray coming from S1 meet this point P here. I call this is ray R2 and this is ray R1. I consider a line from the center which passes from the center. From this point to this point we have D. So this point is in such a way that the distance from this point, this line to this point is D by 2, and similarly the distance from this line to this point is D by 2. So it's from the center. And I consider a reference point, reference line, which goes from this central distance, central point to point P. Now if I look at here, this distance is smaller than this distance. So I can say that S2P is less than S1P. Now I will draw a perpendicular on this ray R1 from this point I draw a perpendicular. By perpendicular I means this angle is 90 degree. I call this point as B. I draw this perpendicular in such a way that this distance and this distance is now equal, like S2P is equal to BP. So here this S1B is the path difference. Like this much distance, this much more distance is traveled by R1 to reach point P as compared to this one. So this is the path difference. Like this ray R1 travel this distance S1B more than this ray R2. So this distance S1B is called path difference. Now we call this path difference S1B is the path difference. I call it delta L, which is basically what? Path difference. Now we have this triangle, and the triangle is the right angle triangle S1, S2B, this triangle. From this triangle we see that this is 90 angle, this is theta, so this will also be theta. This is also theta. So it means that this is the perpendicular, this is the base, and this is the hypotenuse. So we know that perpendicular over hypotenuse is equal to sine theta. Now perpendicular here is S1B over hypotenuse is S1, S2, which is equal to sine theta. S1B over S1, S2 is basically this distance, which I represent by this small d. The distance between S1 and S2 is d. So S1, S2 is d is equal to sine theta. S1B is equal to d sine theta. And this S1B is what? It's the path difference, which I represent by delta L, which is equal to d sine theta. Now we calculate the path difference delta L, which is d sine theta. Now I will stop my video here, and I will continue in the next video. Thank you.